Hey folks, got another example of using conservation of energy when non-conservative forces are involved. Uh, so I've got an example up here. It's a block sliding down an incline. And when we start our watch, the block is already moving at the start point up there. And the block's going to slide 10 meters and it'll be moving at the end of the 10 meters. And I'm giving you some more data. It's the angle is 30 degrees. The coefficient of friction is 0.2. The starting velocity is 5. And the two things we're going to calculate are the final kinetic energy of the block at the end of its movement when it's down here. Okay, it's still moving, and also what is that final velocity down there? Okay, so I'll write out our conservation of energy equation, which is K naught plus U naught plus work non-conservative equals K final plus U final. Now for potential energy here, now by the way, the two locations we're going to look at are A and B, obviously. Okay, so that's our starting and final positions. The first thing we're going to do is there is a K naught, so I'll leave that term there. Is there a U naught? Okay, well, first of all, there's no springs here, so we don't have to worry about that. But there is a change in gravitational potential energy. The block is moving downward. So we have to establish a zero height position for gravitational potential energy. And you could theoretically pick anywhere you want and you'll do it, you'll get the right answer. For me, I'm going to pick location B. I'm going to call that zero height. Okay. So that way one of my potential energy terms will be zero. At point A, though, we are above that point. So there's going to be this term here. There are non-conservative forces acting on the block. So, and at least one of them is going to do work. So I better draw an FBD. Now, at this point, I hope that I can just draw the component FBD and you guys will all recognize it. So on the block, we have the normal force, which is going to point away from the incline perpendicular. You're going to have two components of gravity. You're going to have your mg cosine of theta, and you're going to have your mg sine of theta. And then it's a rough surface, so you're going to have friction pointing against the motion, force of friction. Now, the mg, that's gravity. That is our potential energy term, so we don't worry about those. The normal force is not doing any work because it is directed perpendicular to the motion. So the only force doing work here is friction. Okay, and that's doing negative work because as the block slides down the incline, friction is acting up the incline. So there will be a work non-conservative term, and when it's all said and done, it will be negative. At the end of the motion, there's still kinetic energy because the block's moving, and we're trying to find that number actually. And we're calling that zero height, so that potential energy will be zero. Okay. So the next step is I'll write my formulas out. So we have 1/2 mv naught squared plus mgh. Okay. There's going to be a minus here. Okay. I'll write this out. Force of friction times delta x. So again, don't forget your delta x. It's a common mistake that people will make. And I'm trying to find the final kinetic energy, so I'm just going to leave this as K final. I want to know that number. Okay. Now I'll do one more step here before I start plugging numbers in. We got 1/2 mv naught squared plus mgh minus the force of friction. That's going to be mu Fn, which is mu, and Fn is going to equal mg cosine theta in this case. So we got mu mg cosine theta times delta x, which is d, which is 10 meters. That's going to be our K final. Okay, so the good news is I have everything there except for K final. So we're just plugging and chugging. So we got 1/2. The mass of the book was 4. I believe I gave that to you, right? Oh, nope. Okay, one more given. The mass of the book is 4 kilograms. In order to determine the kinetic energy of the book, I have to give you the mass of the book. So the mass of the book is 4 kilograms. All right, so then we got this initial velocity, which is 5. We got to square that, plus the mass of the book times 9.8. Now, what's the height? It's not 10, right? So what's the height that the book starts at? Well, imagine you got a little triangle here. This is our height. Well, that's going to be, this is d, the hypotenuse of that little triangle. Well, the height's just going to be d sine theta, okay? So this will be 10 sine of 30. Okay, so that's our d sine theta. So that's our H right there. Minus mu, which is given as 0.2, okay, times the mass of the book, which is 4, times the gravity, which is 9.8, times cosine of 30, all that times the distance the book actually travels, which is 10. And that's going to be our K final. Now, real quick, I'll throw some numbers in here. This first number is 50. The second number, I got 196. And the work done by friction is 67.9. That equals K final. Okay, now I want to make a note of this. So the book had 50 joules of kinetic energy to start with and 196 joules of potential. So that total is 246. Okay, so if I asked you at the beginning of the motion how much total mechanical energy did the book have, your answer is 246 joules. Friction robs 67.9 joules of that away from us. So our final kinetic energy, which is our final mechanical energy as well, because we're calling that zero potential energy, should be, I get about 178 if I round it to the nearest whole number. Okay, so that is your final mechanical and therefore kinetic energy of the book. And the final thing we ask for is what's the final velocity? Well, that's really simple. Velocity is root 2 times the kinetic energy over the mass of the book. That's just taking K equals 1/2 mv squared and solving for V. And if you plug your numbers in, 2 times your 178 over the 4, I got 9.44 meters per second. All right, so again, I will reemphasize, be able to not only find a velocity, but be able to talk about the energies and what's going on. You have some initial kinetic energy, some initial potential energy. You're losing a little bit of that due to the work done by friction. You started with 246 joules of mechanical energy. You end up with 178. That entire 178 is kinetic energy because we're defining that position as zero potential. So I hope that example was helpful, and I'll see you in the next one.